2.5 talks about transformations of different functions. So on this first page, we have 6 different parent functions. Okay, we have our linear parent function, which is y equals x. It could be other stuff as well, but that's the parent function. So the parent functions before any transformations, nothing's being added, subtracted, multiplied, or divided. It's just as basic as it can go. The second one is the absolute value parent function. That is a V shape. Okay. The third one is the quadratic. That is the U shape. We have the cubic function, and then the square root and the cube root. So based on your equation, if you have the absolute value bars, if you have something squared, if you have something cubed, or you see one of the radicals, that's how you determine what the parent function is. And so when you go to graph these online, you'll have to select the correct function, and then it pops up stuff. And I have some pictures to kind of show you what it looks like. And so just the first step is picking the right function. Okay. Most of the time it's linear and quadratic. Sometimes you'll see an absolute value, but then I have seen some of the radicals and cubic ones as well. Okay, so transformations. So every transformation, what moves a graph up, down, left, right, is the exact same in every function, no matter what. Okay, so if you have a function plus or minus something, a value, okay, in this case, we have k. If you have plus or minus k, plus k attached at the end, where it's not inside the function, so it's not inside the absolute value bars, it's not inside being squared, it's not underneath the radical. When you have something, that's how you know if it's moving up or down. A plus k goes up k units, a minus k goes down k units. So in these examples, you won't actually have to ever graph anything by hand. You will have to be able to plot some points. Typically, you need about 3 points on these to graph. So typically, it would be where the vertex is, and then 2 other points. Sometimes it's just 1 other point. It just kind of depends. So on this first example, it says, state the transformation that occurs and sketch a graph of each function. So when you look at this first one, okay, you see that there is an x squared. That's what tells you the parent function. That is the highest exponent that's there. So that tells you that our quadratic function is the parent function. So the parent function is the quadratic, which is just y equals x squared. So I'll add that too, just in case. Okay. So if you look back at the graphs at the beginning, that means that whenever this box pops up, this is how it's going to look. Okay. You're going to pick the one that deals with the quadratic function. Okay. If it were to the 3rd power, then you would pick this other one. But since it's to the 2nd power, you're going to pick this one right there. And once you select which function you want, something else you need to make sure of is that you have a solid line. Okay, you won't need the dotted line for a little bit. So you'll make sure you have the solid line and the quadratic as your 2. And then what I think is most useful is if you just plot at the center, the origin, 0, 0, and then you can go and do the transformations from there. Sometimes you'll have to actually like plot where points are. Sometimes you'll have a box that looks like this. So I tried to put those pictures in there because this is where people get the most frustrated and stuff with it. Okay. So, once you plot a point, you could have this box pop up, or you just may have to put another point on there. So I'm going to show you how to deal with both of them. So if we look at this problem, this equation, notice that we have a +2 on the outside. It's not inside being squared, and you will see the difference in just a little bit. So this tells us that this graph is going to be shifted up 2 units. So all that means is from the parent function, every point is just going up. So if we have this point right here at 0, 0 for the parent function, then we're going to go up 2 spots, and it's going to go right there. So it's just going up 2. And that goes for every single point on this graph. So we have some nice points at -1, 1. And then we have another nice point at +1, 1. So each of those points are also going to shift up. So when they shift up 2 units, it goes here and here. And then you can just connect those new points, which once you plot a point, it draws the graph for you, and it will look like that. And so this would be the only graph right here that you have as your answer. The other one won't be there. Okay, but I'm just showing you the parent function. So the red is where you'll start, and then what I have highlighted is how you're moving it if you needed to. Now, if this box pops up and you don't actually have to plot points and stuff, you will always start at the center, but then you will have this, and depending on what transformation, if it's a vertical shrink or stretch, you'll slide this to whatever number. If it's a horizontal stretch or shrink, you'll slide that. But this one, we want a vertical shift, so we're going to go right here. And in this box, you would type in, you would erase this, so erase that, and you would type in a +2, and it would shift it up 2 units. If it's going down, you would type in a -2. If it's a horizontal shift, when it gets there, we'll talk about that. And then if it's a reflection, these are just like boxes that get checked, which we don't have a reflection because we haven't talked about that yet. So you would just type this in, 2, boom, be done, and it should graph. If there's more transformations, then you may have to move multiple things in order for that to happen. Okay. Another backup you have is you could make a table and just plug in some X values and get some Y values to graph if that's how you want to go about it. So what that would look like, you can pick whatever X values you want. But if you plug in some X and Y values, and I won't do this for every table or for every graph that we have, but just showing you that you have options. You could plug in some values. So if you picked -1, if you pick 0 and you pick 1, when you plug them in to this equation, then you'll get the Y value. So if I plug in -1, that would be -1 squared plus 2, which is 3, which is why we have a point at -1, 3. Same concept if we plug in 0, 0 squared plus 2 is 2. And then if we plugged in +1, we would end up with 3 again. So again, that is just a second option to get these values if you don't want to do the whole parent function and moving it up or down. Sometimes that may be easier, especially when there's a lot of different transformations, to just get a couple points and be done. Okay, I will show you how you, once we get into more of the problems, how you get this right here, which is what is kind of like the center of the graph. I'll talk about how you can get that. But there's that. Okay, so that's the first one. So again, you would select the quadratic, and then if this box pops up, you would just type in 2 because there's a vertical shift. Okay. On the second one, so this is just to show you what it looks like if there's a minus sign. So notice on this one, you have more options of the different parent functions that we have. You're not going to worry about the circle until later on. You're not going to deal with a sideways parabola. We don't do that. Okay, so you would have to know here that this one, this parent function, is the absolute value. And that's y equals the absolute value of x. And again, we know that because we see the absolute value bars. The minus 3 is telling us that this function is going down 3 units. And they may add in a vertical translation down 3 or something like that. They may be a little bit more fancy with their wording than I am. So if we refer back to that first page that talked about the parent functions, we would pick this one right here. That is the absolute value one. And again, we would pick the solid line. And if you ever like make a mistake and you're like, I don't know, I just need to start fresh, you can always hit clear. I'm sure this has answers to questions if there's something you're confused about. So this is what that parent function looks like. So typically, anytime I graph, I always start at 0, 0. Because all of our parent functions, if you look back here, all of these parent functions go through the point 0, 0. So I like to use that as like my gauge, and then based on the transformation, I move that point, and then I just move everything else from there. I always kind of let 0, 0 be like the center focus, and then I pick something on this side, something on the other side to get the other values. Okay. So on this one, we're taking all of these x values, or sorry, all of these points, not x values, all of these points, and we're moving them down 3 units. So if we start with this point right here and we go down 3 units, that's going to be to right here, and we went down 3. And then again, you just pick a couple other points. So here's a point here, here's a point here at, again, 1, 1, and negative 1, 1. And so you just move them down 3 units. 1, 2, 3. And that's where the new point would go, and you would connect them. Okay. Now these lines do keep on going forever and ever and ever and ever. I'm just not going to draw them, but you can draw them as far out as you want to draw. It's the same thing. Okay. We're just focusing on a couple points. And again, because it's still like once you move it, it's still down here at 0, 0, or not 0, 0, but 0, negative 3. If you wanted to make a table, these same values would work, and you would just plug it into this equation. What we may need to be refreshed on is that the absolute value always comes out positive. So if I do the absolute value of 1, it's 1. the absolute value of -1 is also 1. Okay, so whatever comes outside of the absolute value will be positive, and then you subtract 3 from it. Okay, the main difference between these two graphs, besides some of the points, is that the quadratic is a U shape, where the absolute value is a V shape. Okay, and so I believe one like this shows up where you select this and then you have to type in the number. And then one like this, where you have more options here, you actually have to physically put some points there. Okay, and again, you can always make a table if you need to. Okay, so that is a vertical shift, vertical translation. It's just going up or down. Okay, then we have our horizontal shift, and this is the one of the ones that mess people up. So notice the placement of our values. Notice that it's inside the parentheses, okay? Versus up here, the K's were on the outside of the parentheses. That makes a big difference. So when it's on the inside, anytime you're dealing with anything inside directly affecting the X value, this is where it starts to act goofy. And what I need you to remember is that these will always act opposite of what they look. And I'm going to explain what that means. But they'll always be the opposite. So what I mean by that, if you look at this right here, this first one, it looks like it's saying minus H. So you would think that it goes in the negative direction. But that minus H, you have to think, nope, that's the opposite because it's on the inside. So really, it's going to the right H units, which is in the positive direction. Okay, so when it's a minus H, you have to think, okay, it's really the opposite. It's trying to fool me, and I'm really going in the positive direction. And then same thing here with the plus H. That looks like it's positive, but it's really going to the left in the negative direction. And the reason behind this is because the formula has a built-in minus sign, kind of like we dealt with on Monday's class with the point slope formula. The built-in minus signs, same thing here. It's a built-in minus sign. So if I plug in a negative number here, the double negatives turn it into a positive. Versus if I plug in a positive number here, it's going to look like a minus sign. So it just is opposite. Okay, so opposite of what it looks like. That's what we need to think about. So, same concept here. I did not put the pictures that pop up. Okay, so we'll just have to make sure that, again, we know the different parent functions. So if we look at this first one, based on the exponent being a 2, that tells me that this is a quadratic. So the parent function is the y equals x squared. That's the quadratic. Okay, so if we look, we see that we have a plus 2 on the inside, and we're not going to let it fool us. We know that it's really not going in the positive direction. It's going in the negative direction. So this is going to the left 2 units. And that's because a negative 2 was plugged into that equation to try to fool you and look positive. So each thing here is going to be moved to the left 2 units. So again, I like to start at this little vertex point. Maybe I should pick this. Okay, I like to start at the little vertex, and I like to just go over 2 units, left 2, to get my new point. And then I would do the same thing with other points on the graph. Okay, so if I had this point, I would also just move it to the left 2 units. And then the same thing with this point, left 2 units, which would actually put me right there. And so then you can connect the dots. I'm not going to draw them too big, but they keep going up and up and up and out in both directions. I probably should not have used red now that I look at it. So let me fix that. Do purple. Okay. So the parent function's in red. The other function is in purple, the transformed function. So for this one, if you try to use zeros as a point to plug in, you're going to get stuff that's graphed over here, and it may not look like a quadratic. So whenever you pick a point, I would always start with whatever this x value is going to be, or the opposite of this x value. And so if I were making a table, the points that I would actually pick, I would start with -2, and I would pick one number on either side of -2 because it went to the left 2 units. So -3 and -1. Those would be the values that I would plug into that, and that's how you're going to get those y values. So whatever the opposite of this is, that's where I would start with my x value. And so you can plug them in. -3 plus 2 squared. -3 plus 2 is -1. You square -1, you get a +1. Okay, you plug in -2, same concept. -2 plus 2 is 0. 0 to the second power is 0. And then you plug in -1. -1 plus 2 is 1. 1 squared is 1. But the numbers that are causing the transformation, that's basically telling you where that center or vertex is going. It's how is it moving from 0, 0. Okay. This next one is a parent function we have not graphed yet. So because this is just the normal square root symbol right here, there's no number sitting on this ledge. Eventually you may see a 3 sitting there or something like that. That means that this is just the square root parent function. So that's y equals the square root of x. Again, that's the square root. This one to me looks like an eyebrow. Okay. So notice how the number is on the inside of the radical. If there was a vertical transformation, it would be on the outside of the radical, something over here. So inside, when it's on the inside like it is, that's how you know that it's moving left or right. And so since it's moving left or right, we have to think opposite of what it looks like. So it looks like it's a -3, but really we know that that means it's going in the positive direction. So this is going to the right 3 units. Again, showing you the difference or what it looks like again on the inside of these functions. And that's how you know that it's, again, going left and right. And once we put both transformations together, you'll see that even more. So with this right here, again, you can take some points. So think about this going through perfect squares. So our perfect squares are 0, 1, 4, 9, 16, 25, so on and so forth. And so we want those numbers to be able to take the square root of. If not, it's going to be a decimal, which is fine. It's just you can't be super exact with decimals. So if we look, again, it goes through 0, 0. So if we really wanted to, we could just start there and just move it to the left 3 units. Okay, so if we're going to the left 3 units, 1, 2, or sorry, to the right, I would have my new point right there at 3, 0. Then we have a point at 1, 1. You can move that as well, 3 spaces. 1, 2, 3. That's where your new point would go. And then if you look at 2, 2 is not a pretty point. So I wouldn't try to move the y value at 2 over because that's not pretty. If you look at the y value at 3, it's also not pretty because those aren't perfect squares. But once you get to 4, notice that it's crossing at 2. So that's a nice pretty number. It's a whole number. And so I would take that and also move that 3 spaces to the right. And once you have enough points, you can connect the dots. This part is not part of the graph. Those arrows that I'm showing that are moving, that's not part of the graph. That's just showing you that we're moving them. So this right here would be our graph. And again, if you wanted to plug in some values, you can. Because we started at 0, 0 and we took it to the right 3 units, I would start with 3. And this time, so this is where knowing your parent function is useful. This is one of the only functions that it doesn't have values on both sides. So what I mean by that is if I go back up here, if you see this first linear function, notice how I have graph on both sides of that 0, 0. The absolute, I have a graph on both sides. And so that happens for all of them except when it's the square root function. I only have values on this side. So since we moved it to the right 3, if I were to make a table, okay, and this may be some trial and error stuff. So if you plug in a number and it's not going to turn out to be a pretty number, then I wouldn't stress about it and I'd move on to the next one. So if I were plugging in some values here, that's b of x, I would start with 3 and I would do 4, 5, 6, 7 in hopes that at some point I'm going to get some pretty numbers. So when I plug in 3, we should get 0 because that's that point. Okay, so that would be cool. If we plugged in 4, 4 minus 3, I guess I should maybe write it out. Let me not be lazy and skip some steps. Let me write stuff out. Let me go back. If we plug in 3, we would have 3 minus 3. That would give us the square root of 0, which is 0. I can graph that. We can graph 3, 0. If we did 4, it would be 4 minus 3, which is the square root of 1, which is a nice pretty number. We can graph that. But when we plug in 5, we would get 5 minus 3, and that would give us the square root of 2. The square root of 2 is not a pretty number, okay? It's about 1.4, not pretty. Why do I know that? Because it reminds me of Valentine's Day. That's all I think about. Okay, the 2 and then the 1.4, Valentine's Day. Um, if we plug in 6, we would get 6 minus 3, which is equal to the square root of 3. That's also not a pretty number. That's like 1.7. St. Patrick's Day, 3, and then the 1.7. I wouldn't graph those. I wouldn't stress about those values. But if you plug in 7, then you should get another pretty number. Oops, not 4. And so you would get the square root of 4, which is 2. And so I would only focus on graphing these pretty numbers and not worry about those decimal ones. Because again, you can't really graph decimals exactly. Okay. So really that's all that we're doing. If you prefer a table, you have a table. If you can start with the parent function and shift it, then that's cool. Once we get into some of the reflecting and the stretching and the shrinking, then the parent function may not be as helpful, and the table would probably be our best bet once you get into like the overwhelmingly, unless this pops up and then everything's made so much simpler because you don't actually have to plot, you just have to plug in whatever's happening here. Okay. Anyways, so that is the horizontal transformations, shifting left and shifting right. So in this example right here, this is showing you what it looks like when you combine both of those together. So we have h of x equals the absolute value of x minus 2 and then minus 4. So this is to clearly show you the difference between something that is inside the function versus outside the function. Okay, so if we look at this again, these absolute value bars right here tell us our parent function. So our parent function is y equals the absolute value of x, which is the absolute value function. I'm going to abbreviate absolute. Okay. And so we have two different transformations. The first transformation is this inside piece right here. Again, that's where you have to remember to think opposite. That's where you have to remember to think opposite. So since it's the opposite, it looks like it's a minus 2, but it's really going in the positive direction. So it is going 2 units to the right. And then this minus 4 on the outside is going down 2 units. Or sorry, 4 units. So 4 units down. Okay. And so when you have this, these are going to be questions that end up either being like multiple choice and you have to select the one that has all the right. So they'll have right 2 units and down 4 units. They'll have left 2 units, down 4, right and up, and all this other stuff mixing and matching. So you just have to read to make sure it meets everything. Or it would be a problem that you have to select all the different transformations and it just gives you a big list. Okay. Now with these, when it comes to graphing, especially if you want to use the table versus the parent function, how you figure out what x values you need to start with, and I'm not going to actually go through the table part, but I'm going to at least give you kind of a starting point so that way you can practice plugging in some values. So here's my x, here's my h of x. These movements tell you where your center is going to be. So if we're starting at 0, 0, I'm going to the right 2 units, and then I'm going down 4 units. And so this is my starting point down here. So again, I'm going to the right 2, down 4, and so the very center of my graph is going to be right there at 2, -4. So it's kind of giving you coordinates. So you know for sure you're going to have the point 2, -4 on your graph. You can pick an x value on the left side, you can pick an x value on the right side. And then you plug them in and do the math. But again, the transformations are telling you one coordinate that you have. As long as you're not multiplying or you're having a vertical stretch or compression, that's when it's a little bit different. But we haven't got there yet, so when it looks something like this, that tells you that first point. So negative or 2, -4 right here. And then you can either, again, plug in points here or plug in values into the equation to get those y values, or you pick a point on the parent function and you move it again, right 2, down 4, and you put a point there. So I'll leave 1 on there, so we go right 2, 1, 2, 3, 4, and down 4. And then again, you would do that with another point. So if I had this point right here, right 2, down 4, 1, 2, 3, 4, I'd have a point right there. Also, you may start to see that some of these have patterns or they're symmetrical. So what happens on one side happens on the other side. If you can recognize those, that might save you some time. But again, if you see, we have the x value of 1 right there, and then the x value of 3 right there. So those would be the points that you get if you plugged them in. So if you want to practice plugging in points to make sure you're good, you should get the same value. Okay, that's if you actually have to plot them yourself. If this screen pops up, okay, you would do your vertical shift, which was down 4. So our vertical shift on that problem we were just working would be -4, and your horizontal shift would be a +2 because we're going in the positive direction. So if that pops up, that's what you would plug in. And then you would hit OK, and it graphs it for you. So again, the vertical shift was down 4, and then right 2. So we would plug those in, and then it would graph. Okay, so that's that. So I want you to take a second and look over what we've done so far, see if there's any questions about anything, if I need to clarify anything. So I'll give you a quick second. Any questions or anything that I need to clarify between the 3 examples we've done so far? Okay, cool. Okay, the next one is talking about reflection. So there's specific parts if in that box that pop up that deal with reflections, and you may not have to worry about this. And then there's things that may not pop up and you will have to worry about it. So there's 2 different types of reflections. One reflects across the x-axis and one reflects across the y-axis. Okay, when it's reflecting across the x-axis, there's going to be a negative in front of the function. Okay, and so that goes there. And so whenever it comes to dealing with the values, all of your y values change to the opposite signs, which means if all your y values were positive, they're all negative. If all your y values were negative, they're now all positive. If it's mix and match, they just change to the opposite. Okay, that's when it's out in front. If it's on the inside, that's when it's reflecting across the y-axis, and all of the x values change to the opposite sign. Y values stay the same, your x values just change to be positive or negative, whatever the opposite is. Okay, so whenever you're changing the signs, the other one that's not being affected stays the exact same. Okay, and again, if that box pops up, I'm gonna scroll back up. If the box pops up, whichever one it would be, that would be what you select. And you just check the box, click on it, it puts a check or an X. And that's how you would do that reflection, and you wouldn't have to actually worry about making a table or anything. Okay. So on example 4, just to show you what this looks like. Okay. On A, we have negative x squared. One thing I do want to say is that negative x squared is not the same thing as negative x quantity squared. Those are two different things. And that's something that might be confusing, might not be. Okay. This first one, only the x is being squared, and then it's being multiplied by a negative 1. And the second one, the negative x is being squared, which means you have a negative x times a negative x. So those are not the same thing. So in this case, we have it on the outside of the function. And since it's on the outside of the function, if we look back up here, the outside of the function deals with it crossing the x-axis. Okay, so this is a reflection over the x-axis. And I did forget to state the parent function. So this parent function is y equals x squared, which is the quadratic function. The parent function is when you basically take away anything that's being added, subtracted, multiplied, or divided. Take away any numbers, and what's left over is the parent function. Okay, so with this right here, all we're going to do is we're going to take some of these x values, or some of these points. So I'm going to put a point at 0, 0, negative 1, 1, and 1, 1. To get the reflection, all you're going to do is you're going to change your y values to be negative. So at this point right here, at negative 1, 1, that y value is going to change to a negative. And so you get negative 1, 1, negative 1, negative 1, negative 1. Okay, so maybe we can also make a table that just shows the value so you can see. So we did negative 1, negative 1. Then we have the point 0, 0. 0 is neutral. It can't be positive. It can't be negative. So it's just going to stay 0, 0. And then we have the point 1, 1. And that turns into 1, negative 1. And that's how we get this point. And so then you have your parent function. Boom. So only your y values change to be the opposite sign. And it shows that it's a mirror image of the graph, and it's just flipped over that line. So if you fold it in half, they should line up. Okay. looking at part B. So notice now this one is on the inside. Okay, so our parent function is the square root function. Okay, the square root function. And because it's on the inside, that means it's a reflection over the y-axis. So when it's a reflection over the y-axis, only the x values change to the opposite sign. Only the x values change to the opposite sign. So if we have some points here, so again, 0, 0 is a nice point. Maybe I should write the points in here. I don't know. Maybe this might allow you to see it. We have 1, 1 as a point. And then we have 4, 2. So the only thing that will change is your x values will turn negative or to the opposite. Right now they're all positive, so they're going to turn negative. So that means we would have the point 0, 0 still. But instead of 1, 1, it's going to be 1 or negative 1, 1. So negative 1, 1. Instead of the point 4, 2, it's going to be a negative 4, 2. Maybe that might be a little better seeing it that way in the table. And so you get that shape. Sometimes it's just a multiple choice question and you have to pick the best graph that goes with it. Okay. Now, when you start dealing with things on the inside, that's when it can get a little tricky. So this is just extra information. I like to make up problems sometimes when I see that they kind of fit. If there was a reflection over the y-axis and a horizontal shift, you have to kind of be a little bit careful with that. So an example, if we had f of x equals the square root of negative x, we'll just go plus 2 like that. If you had something like that, we may think that, yes, this is a reflection over the y-axis and it's going to the left too. But you would be wrong and then you get really mad, like, why am I getting this wrong? So when you have a reflection specifically on the inside and a shift, what you have to actually do is you have to factor out the negative sign. And so when you do that, it turns into this. And so now you can see that there is a reflection over the y-axis and it's actually going to the right too. It's that negative was putting it in disguise. Okay, so if you see something like this, you have to make sure that it's not distributed. And I try to avoid those problems because they just seem to be more complicated than they need to be. So if you see something that looks like this, then it does need to be rewritten before you can state the transformation. Okay, these are the same graphs. Okay, so it would be shifted to the right and then it would be reflected. Okay, so we have that. That's just extra. Again, I try to avoid those, but sometimes they pop up and I don't realize it. It happens to me all the time when I assign a homework assignment. I'll do 10 of the problems and then I assign it to somebody and then it's not what I did at all. So I tried to avoid that. Okay, the next one is vertical stretching and shrinking. So vertical stretching is, I want you to think about if you had like Play-Doh or something and you were stretching it. When you stretch something, it gets skinny. And then if you shrink it or squish it together, I like to think of compressing. If you compress it together, it gets wider. Okay. If I happen to say it, I may say for shrinking, I may say compression or compress. Okay. To me, that sounds better than saying shrinking. Um, all in all, these are vertical dilation. So again, it's stretching it out or pushing it down. Okay. Where it like overflows. Okay. This is when you have a value in the front, in the very front of the function. So it's not in the parentheses, it's not in the radical, it's not in the absolute value bars. It's out in the very front that you do everything else, and then you multiply by this value. Okay. So that is a vertical stretch and shrink. So if these values are, you have two options. If A is greater than 1, it causes a vertical stretch. And the vertical stretch means that each y value is multiplied by A. And then if A falls between 0 and 1, that is causing a vertical shrink, where each value is multiplied by A. Now, the reason that there is the absolute value bars there is because up until this point, well, right before this, we had negatives, which cause a reflection. So if you see a negative A value, that's actually two different transformations. The negative causes a different transformation, that's that reflection. So that's why these absolute value bars are right there, is because the stretch and shrink come specifically from a positive A value being greater than 1 or between 0 and 1. Okay, a negative A value is actually two different transformations if it's like -2 or -3. And I believe I probably put an example in here somewhere that deals with that. Okay, so if we look at this one, same concept. We have t of x equals 2 times x squared. So notice it's not inside of parentheses. This is my A value. My parent function is y equals x squared, that quadratic value or that quadratic function, that quadratic graph, okay, that U shape. That 2, so A is equal to 2, and 2 is greater than 1. Since our A value is greater than 1, that means that we have a vertical stretch of 2. So that means that all of our y values are going to increase by like being multiplied by 2. Okay, so on this first function, we have our parent function here. We have our original, so it starts at 0, 0, and then we have -1, 1, and 1, 1. A vertical stretch only affects the y values. It only affects the y values. So this y value, this y value, and this y value are being multiplied by 2. X is staying the same. So when we multiply 1 by 2, if we times it by 2, that means I'm going to have a new point at -1, 2. When I multiply 0 by 2, I get 0. That's why we like 0. If we multiply this one times 2, we get 2. So we have a point right here. If we had other points on here, so we also have the point 2, 4. So if we had the point 2, comma 4, and we multiplied the y value by 2, we would have 2, comma 8. It's just not on our graph. Okay. You could also make a table, plug in values. If you go that route, you have to remember order of operations, where you square the number first, then multiply by 2. Okay, but you could go that route as well if you wanted to make a table. I like to make sure I give y'all options so you can do what makes the most sense to you. So if you wanted to go this table route, again, I would start with 0 in the middle, put a number here, pick a number here, and go. Okay, and again, square, then multiply, order of operations. Exponents before multiplication. If it's a problem where the box pops up, so let's go back to the box. Then for this, you make sure that you're moving the vertical one, and you would just slide this in any direction. So you would slide it until the number 2 pops up, and then you're good and you're done. Okay, so again, you would slide to wherever 2 is and then press enter, okay, or however that goes. Okay, so you have that. So again, you can make a table, you can move the points. I guess I should connect the dots. And all it does is it stretched it and made it more narrow and a little bit more skinny. Narrow and skinny. Okay. So now the second one, notice now we have a fraction in front. And I try to steer away from saying, oh, fractions are always going to be shrinks and whole numbers are always going to be stretches. But that's not always the case, because you can have an improper fraction, which would actually be a stretch. So I don't want to necessarily say that, but 1/3, 1/2, anything that's less than 1 but greater than 0 is going to be that shrink. So this one right here, our a value, it has the same parent function, but our a value this time is a 1/2. 1/2 is between 0 and 1, which is why this is a vertical shrink. Of 1/2. So now all of your y values will be multiplied by 1/2 or cut in half, or you find half of your y values. So you would probably want to pick y values or points that had y values that were even, because even dividing by 2 or multiplying by 1/2 is easier than when it's not. Again, multiplying by 1/2 is the same thing as dividing by 2. Those are the same concept. So if I have some points, I'll do them on the table and then I'll write some points. If you use the table, this is w of x. I would always start with 0, 0, because that's a nice pretty point. Okay, but if you pick 1 or -1 and 1, you're going to get fractions. So maybe you don't want to deal with those. So then on this one, I would probably use -2 and +2 just so I get some nice whole numbers to graph if you had to physically plot points. Okay. So again, there's that, or you can look at it this way, same concept, get some points from here. So there's 0, 0. I'm going to go ahead and do 2, 4. and negative 2, 4. And so again, with a vertical shrink or a vertical dilation, that's what these are, you're going to multiply the y values by that value. So we're going to multiply by 1/2. So 4 times 1/2, or half of 4, is 2. So the new point would get moved to 2, 2, negative 2, 2. 0, 0 is going to stay the same. And then half of 4 again is 2. So then you get that graph right there, which I'm not very good at connecting the dots. But again, it's showing you that this graph right here was stretched and it got more narrow. And then this graph, it was kind of compressed. And that's why it got a little bit wider than the parent function. Okay. So if you want to take a second to look over that to see if you have a question about anything, something that maybe I didn't cover well. So anybody have any questions about anything? Okay. And I'll keep on keeping on. We're almost done, I think. Oh yeah, we're almost done. Woo! Okay, this last one, this is like the grossest one of them all. I saved the best for last. Okay. It is the horizontal stretching and shrinking. The reason why this one is gross is because it's inside, directly touching the X. And anything that is directly touching the X causes issues for us. Okay. So here we go. The B value. If B is greater than 1, then it is going to shrink the graph horizontally. It's opposite. The reason because that is because you end up dividing each X value by B, and that's why it's weird. Okay, so it really looks like, oh, the B value is greater than 1, but really it's a horizontal shrink of 1 over B. That's why it's weird, because we have to divide our X coordinates by B. If B is between 0 and 1, it's actually stretching the graph of F horizontally. And so you divide each X coordinate by 1 over B. And so if you're dividing by a fraction, that makes the number bigger. Dividing by a fraction makes the number bigger, which is why this is a stretch. Okay. So again, now we're thinking about pulling it apart horizontally or pushing stuff together horizontally, compressing it or shrinking it versus pulling it apart. So if it's a shrink, it's going to get more narrow. And if it's a stretch, it's going to get more wide. Okay. So, again, these don't come up very often because they are confusing. Okay. So here we go. Both of these functions that we have, for example, 6, the parent function is the absolute value. So I'll just write that one time for both of them. That's the absolute value. Okay, so on this first one, we have a 2 on the inside. And same thing goes for it being a positive number. The negative causes the reflection. So our B value in this one equals 2. 2 is greater than 1, which means we're actually going to have a horizontal shrink of 1/2. 1 over B. That's the dividing by B part. So we're really going to multiply our x values by 1/2 or divide our x values by 2. Okay, so dividing by 2 and multiplying by 1/2 are the same thing. Dividing by 2, multiplying by 1/2 are the same thing. So we're going to take some of these points here. So I'm going to do pretty points. I'm going to kind of make sure that we get some nice pretty numbers. So I'm going to do -2, 2, of course, 0, 0, and then again 2, 2. So again, you can think of this as either multiplying by 1/2 or dividing by 2. Those are the same thing. So this time it's affecting our x values. So each of those x values are being multiplied by 1/2 or divided by 2. So if we do this, we have, let's see, -2 divided by 2 is a -1. If we multiply by 1/2, we still get a -1. So that's going to turn into a -1, 2. We love 0, 0 because it stays the same. If I take 2 and multiply by 1/2 or 2 divided by 2, that would give me a +1. So I would get this point right here. And then you connect them and notice how it was compressed or shrank in. Okay. You could also make a table and plug in values. If you plugged in 1, 2 times 1 is 2. Absolute value of 2 is 2. And we have the point 1, 2. Same thing. If you plugged in -1, 2 times -1 is -2. Absolute value of -2 is 2. Okay. So again, you can always make a table, just like everything else. On this one right here, the next one right here, we have the 1/2. Okay. So my B value is equal to a 1/2. 1/2 falls between 0 and 1. So this tells me that this is a horizontal stretch of, if I'm dividing by 1/2, that means that we end up multiplying by 2. Dividing by 1/2 is really multiplying by 2. Just like dividing by 2 is multiplying by 1/2. It's the opposite. Okay? So if you think about it that way, you can really multiply by 2. That way you don't have to worry about dividing by a fraction. That's also the multiplying by the reciprocal part. The reciprocal is flipping that. We talked about that last class with the perpendicular lines. Flipping that fraction, that's the reciprocal. Same concept here. Okay, it just makes your multiplication part just a little bit easier. Or division, or however you want to think about it. So same concept. If you want to make a table, but you really just need some points to start with. Okay, so we'll do 0, 0, and this time we can do -1, 1, And then we can also do positive 1, 1. And so again, dividing by 1/2 is the same thing as multiplying by 2. Dividing by 1/2 is the same thing as multiplying by 2. So this time we're going to take these x values and we're going to multiply by 2 or divide by 1/2. It's all the same. We love 0, 0 because it stays true to itself. If I multiply negative 1 by 2, or if I divide it by 1/2, I get a negative 2. If I take positive 1 and multiply it by 2 or divide it by 1/2, I get a positive 2. And so it just looks like the graph has been stretched out a little bit more. Okay, it's been pulled apart horizontally. Okay, I would not stress about this part too much if you're like, what is going on? It's just really, it's on the inside, so it's acting opposite than what it looks like, just like the horizontal shifts. Okay. When it comes to transformations, you can do these in this order right here: stretching or shrinking, reflecting, horizontal shifts, and vertical shifts. If it comes down to you having a whole bunch of them and you're actually having to plot points, my suggestion is finding that vertex, that center where 0, 0 would be based on the horizontal and vertical shifts. And then I would just make a table. Okay, I think it gets really confusing if you're trying to do all of these transformations in one. I would just make a table, plug in some x values, and evaluate it that way. I think that's the safest way to go about it. But if you get this question and these pop up, I want to make sure that you know where all of these buttons and clicking goes. So I'm going to show you this. So this right here is our function. The parent function, because there's a squared, is the quadratic, which means you're using this graph or that feature right there. Again, make sure you have the solid line. Okay, so now there are 4 different transformations. Okay, so I'm going to color coordinate each transformation. The first one, we have this minus sign. Then we have this 2. We have this +3. And then lastly, we have that -1. So the minus sign, remember, that's our reflection. Over the x-axis because it's out in front. So that means that you would check the box at the bottom. Okay. Then that 2, it's out in front. That is our vertical stretch. By 2. Okay, that's why we think about the absolute value and you don't consider the negative to be with the vertical stretch or compression. That's where people mess up. So that 2 being by itself, it's greater than 1, so it's a vertical stretch. So that means right here, on this one right here, you would move this to be 2. So wherever 2 would be, 2. You would slide it till it says 2. Then we have the +3, remember opposite, and that this is actually going to the left 3 units. So for our horizontal shift, because it's going to the left, you would actually plug in a -3, so it moves to the left. And then the last one is going down 1 unit. And so you would plug in a -1. And so you would do all of that and then Press OK and it graphs it for you, and then you're good. You would not mess with this one right here because we don't have any horizontal stretch or shrink. Okay, so that's the end of 2.5.